Hi everyone, welcome back. This is section 17.3. This is the first video in section 17.3, and in this section we are going to be taking a look at finding maximums and minimums. All right, so the objectives for this section are to define and to understand what an extrema is, define the discriminant, which is the tool we'll use to find those extrema, and then go ahead and find some. All right, so the formal definition for extrema says, and I'm going to start right here with this paragraph. It says, let the point AB be the center of a circular region contained in that xy plane. Remember, the xy plane here is our domain for our function. Then for the function z equals f of xy, defined for every xy in that circular region, the point f of AB is a relative maximum. That value f of AB is a relative maximum if it's bigger than all the points around it. Okay. Now, this is kind of a weird definition, but if we think back to our definition of maximums that we had from 212, from your previous calculus course, suppose you had a function that looked like this. Now, we would say that this point right here represented a maximum, even though there were plenty of points over here that were bigger, because the way we defined it is we said for some little interval down here, for some interval from an x1 to an x2, that this point was the biggest on that interval. And we did kind of the same thing over here. We said, hey, that's a minimum, because for some little interval down here on the axis, it's the lowest point. Even though there are plenty of points over here lower, we don't care. We just wanted to say it's the lowest for some little interval on that x-axis. Okay? Well, in three-dimensional space, we pretty much have to do the same thing. But what we're going to say then, rather than intervals, we're going to say, hey, make a little disk, a little circular region down here. And if that point AB, which is in that disk, gives you the highest z value, then we're going to call it a maximum. And if you make a little disk and that point AB gives you the lowest z value, then we're going to call that point a minimum. Right? So our job in section 17.3 is just to find these maximums and minimums. The formal definition is all this stuff about circular regions, and basically all it boils down to is a relative max or a relative min is a high point for a small part of the graph or a low point for a small part of the graph. And we're not talking about absolutes here. We don't worry about those in three-dimensional space. Okay? All right, so how do I find them? Well, the definition says that if a function has a relative max or a relative min at a candidate point AB, then the first partials will both be equal to 0. Now, I want to focus on an important word in that definition, and that's the word and. We are saying that both of them are equal to 0. So it's not a matter of just setting one equal to 0 and solving. It's writing a system of equations and then making that system of equations be set equal to 0. Okay? Now, unfortunately, though, this is an if-then statement, so it doesn't quite give us a true definition that we can work with because it's not sufficient, because this thing can happen. You can get something that looks like a Pringles chip, where you've got a point on that, and that's going to represent our AB from that definition. And in one direction, it's a minimum, but in the other direction, it's a maximum. And unfortunately, at that point, both f sub x will be 0 and f sub y will be equal to 0. So it is possible to have a point on your graph where the partials are both equal to 0, but that point is not a max or a min. So what does that mean for us? Well, it means that the test or the steps that we're going to have to use to find our extrema is just going to be a little more complicated. Now, if you're the type of person who likes to think of things in terms of steps, this will be step 1. Step 1 is going to be to find the first partial for x and find the first partial for y, set them both equal to 0, and then solve that system of equations. That system of equations is going to give us what we're going to refer to as our candidate points. How do you spell candidate? Candidate? I don't know. Those are going to give us our test points. There we go. I can spell that word. So when I solve this, I might get one answer, I might get two answers, I might get 3 or 4 or 5. It doesn't really, there's no rule that says you will get this many answers. It's just going to give us a bunch of points. And then we're going to take those points and we're going to go test them. The way that we test them, and we'll call that step 2, is we evaluate each point in something called the discriminant. And the discriminant is the second partial x at your test point times the second partial y at your test point minus the second partial xy at your test point squared. Okay? So if I find 5 points over here, I'm going to do this thing 5 times. If I find 2 points over here, I'm only going to have to do that thing 2 times, right? Now, once I do this, once I plug in numbers for a and b, this is going to give me a value for the discriminant. And then I'll go down here to step 3, which is where I use the value of the discriminant and the values of the partial derivatives to determine whether I'm looking at a max or a min, right? If the discriminant is greater than 0, I either have a maximum or a minimum, depending on whether the second partial x is greater than or less than 0. Okay? So I'm looking at a maximum, that's this first one right here, a relative maximum, if the discriminant is positive, but xx is negative. I'm looking at a minimum if the discriminant is positive, but xx is positive, and xx is positive. I'm looking at a saddle point if the discriminant is negative, and if I get the unlikely situation where the discriminant is 0, the test doesn't tell me anything. It doesn't tell me whether it's a max or a min. If the discriminant is 0, basically what you have to do is you have to figure out some other way to do it. Now for 3D stuff, you could then graph it, because you know what point to look at, you know what the point is, and you could go look at the graph and say, hey, is that a max or a min? But if you have more than that, or if it's a complicated graph, then that's not really a good way to do it, right? There are by-hand mathematical techniques for dealing with this situation, but they are beyond the scope of this course, so we won't be worrying about it. So this is unlikely to happen to us. But if it did happen to you, you would just go take a look at the graph at that point AB, because you know where it is, because you used it to find D. Go look at the graph and determine whether that's a max or a min. Okay? So, step 1, solve f of x and f sub x and f sub y both equal to 0. Step 2, eval D. And step 3, check the rules. Okay? This little flowcharty thing right here is going to become incredibly valuable to you for the rest of this section, because every single time we go back to this, we go back to this, we go back to this. Okay? All right, let's take a look at an example. My job here is to find all the points where the functions, because there's a bunch of these things, have any extrema or saddle points. All right, so step 1. I need to find the first partials and set them equal to 0. So the first partial with respect to x, first term is going to give me 6x, the second term is going to give me negative 4y, the third term gives me 0, the fourth term gives me 6, the fifth term gives me 0. First partial with respect to y, first term gives me 0, second term gives me negative 4x, third term gives me positive 4y, fourth term gives me 0, fifth term gives me 0. Okay? Now that I've got my 2 partial derivatives, I'm going to take both of these and set them equal to 0. So that's going to give me 6x minus 4y equals negative 6, and negative 4x plus 4y equals 0. If you're wondering where the negative 6 came from, I took the positive 6 and moved it to the other side when I set it equal to 0. Okay? I now have a system of equations, and it appears to me that this is a linear system, and that the coefficients for the y variables are opposites. So I'm just going to solve this by using elimination, meaning I'm just going to add these 2 equations together and I get 2x is negative 6, which means that x is negative 3. And then I'll do a back substitution. I'll choose the second equation, so that gives me negative 4x times negative 3 plus 4y equals 0. That gives me 4y equals 12. And so y equals, negative 12, sorry, negative 3. So my test point, I only have one this time, is the point negative 3, negative 3. Now I just want to stop here for a second and make sure I've done this right, because doing any work beyond this is going to be a waste of time if I made a mistake anywhere in here. So is this right? Let's see. 3x squared gives me 6x, negative 4xy gives me negative 4y, 0, positive 6, 0. That's good. Is this one right? 0, negative 4x, 4y, 0, 0. So that one's right. So then this is good. Add those together, 2x equals negative 6, negative 3. That's good. I feel good there. That's positive 12, but when it moves over, it becomes negative 12. So I feel good there. So I'm good to here. Okay. Now I can move on. Now I'll move on to step 2, where I have to evaluate the discriminant. Now the discriminant at a point AB is equal to the second partial x at the point AB times the second partial yy at the point AB minus the xy at AB squared. So then plugging in our only test point, well wait, I can't plug it in yet because I don't know these. So I got to find those. All right, so what is f sub xx? From the green one up here, I get that that's just 6. Okay. F sub yy. From the blue one, I get positive 4. And f sub xy, or f sub yx if you prefer, is going to give me negative 4 either way. Now this is nice because since these are just constants and there's no variables involved, then the value of the discriminant is the same no matter how many test points I have to test. I only have one to test, so it's a big yay, but it doesn't really help me much. Okay, so then the discriminant for the point negative 3 is going to be 6 times 4 minus negative 4 squared. 24 minus, was that 16? 8, which is greater than 0, right? Because this is what really matters. The value of it doesn't really matter. How is it bigger than 0 or smaller than 0? So now I'll move on to step 3. Step 3 is then where I go and I take that value and I go back up to the rules and I see what it means. So let's see. I'm going to erase all this extra junk in here because it's looking kind of ugly. Come on, there we go. Okay, so I have a discriminant of 8, which is greater than 0, so I'm one of these two. I'm either looking at a max or a min. The second partial xx was 6, so that means it's greater than 0, so I am looking at a relative minimum. So now I can come down here and I can say that we have a relative minimum at negative 3, negative 3. Now, if they ask for the minimum value, then what I have to do is I have to go back and plug that in and see what it is. So what is f of negative 3, negative 3? Well, our function was 3x squared minus 4xy. So 3 times negative 3 squared minus 4 times x times y plus 2y squared plus 6x. So plus 2 times y squared plus 6 times x minus 10, right? Yeah, minus 10. So let's see, this is going to be 27. 3 negatives, that means this is a negative. 3 times 3 is 9 times 4 is 36, so minus 36, plus 18, minus 18, minus 10. Those cancel. That and that will cancel and give me 17. 17 minus 36, so 30, 20, negative 19. So I have a minimum value of negative 19. Now, of course, if I was uncertain or uncomfortable with my solution, I could always go and take a look at the picture of this one, so it should be pretty straightforward. And so let's go ahead and take a look at the picture. And there's the graph of this. And if we look straight down on it, you'll see that it looks like there's a minimum about negative 3, negative 3. Let me spin it around so I can see it. This thing is so touchy. Okay, we're there. There. And it looks like that minimum's about negative 3, negative 3, and negative 20. Unfortunately, there's no easy way to poke at this thing and come up with the answer. But it looks like it supports what we got in our graph, in our math. All right. So that was, wow, what was that? That was 16 minutes, and we managed to do one problem. I have a bunch of definitions too, but I'm going to stop the video here. We'll come back and we'll do part 2, and we'll just continue to do more and more and more and more examples until we get to 17.4. Okay? All right, I'll see y'all back for part 2.